All right, welcome to part 2 of the Geography of Regionalization modules. The cat joined us for part 1, and part 2 we are joined by Tyga the Labrador. So say hello to Tyga. Tyga, say hi. Or just lie there and be lazy. All right, well, getting back into it, this is a continuation of our discussion on patterns of species distributions. We covered cosmopolitan and endemic species distributions in part 1, and in part 2 we're going to talk about disjunct distributions. And the reason that I pulled out disjunct distributions is because they're a great distribution pattern for thinking about how historical events, how geological events, how time has influenced present-day patterns in species distributions. So, quick definition, a disjunct distribution is when closely related populations, species, or taxa, higher taxa, occur in multiple regions on the planet that are widely separated. And again, they reflect past events most often. So I'm going to show you a few examples. And I've only got 3 examples here to show you. What I want you to do is, for each of these examples, I want you to have a look at this distribution map, and then I want you to pause the video, and I want you to think about that distribution pattern and see if you can come up with hypotheses or explanations for why this distribution pattern exists. So the first example that we're going to talk about are Nothophagus, so southern beeches. So these are a group of deciduous tree species. They are found in eastern Australia, parts of eastern Australia. They're found in New Zealand. They're found in western South America. So this is where I want you to pause the video right now. So I want you to pause the video, and I want you to look at this distribution and jot some notes down and see if you can explain why this distribution pattern exists, or why this distribution pattern might exist, rather. There are a couple different hypotheses you can come up with. And think about how you would go about testing that. If you were a biogeographer and you were interested in explaining this distribution, how would you go about testing which hypotheses might be correct? So hit pause now. All right, so coming back, let's have a look at this distribution pattern. So what are some of the first things that we notice? Well, we notice that this species is found in coastal regions. It's not a species of tree that we find in the interior of the continents. So when we're thinking about, so we have a coastal species, it's a tree species. Plants tend to use passive dispersal means. Coastal distribution, passive dispersal, one of the things we might ask is maybe this species has a passive dispersal mechanism over water, so hydrochory. That's one hypothesis that you can test, and that's one that has been looked at and found to be inconsistent or incorrect. So the other hypothesis that you might use to explain that is maybe this is due to the result of plate tectonic activity. So we know that this is the position of the continents today, but it hasn't always been like that in the past. And we know that the continents at one point were connected to one another in supercontinents. So maybe this distribution reflects the tectonic history of this species. Maybe the continents, maybe if we were to look at the formation of the continents through geologic time, we would see that this species once had a much more continuous distribution when these continents were connected to one another. So one of the things that we would have to know in order to confirm whether this hypothesis is correct is that if this distribution is explained by plate tectonics, then this lineage would have to be older than the breakup of the continents. So if this is a newly evolved species that evolved after the continents divided from one another, when they weren't connected, then you can no longer invoke that hypothesis to explain why this disjunct distribution exists. And I'm not sure the answer has fully been worked out, but the evidence so far is consistent with this being related to the tectonic history of the continents. All right, moving on to our second example. We're back in North America and we're looking at the mole. So there's a dark pink and a light pink. Those are two subspecies of mole. We're looking at this distribution. We can find we have an eastern population and a western population. So again, pause the video, take a minute to think about why this distribution might exist. Okay, so I'm going to assume you've given it some thought, you have your ideas. Now you've resumed the video. I'm going to point out some things that maybe you've already thought of or maybe you haven't thought of yet. So I'm going to tell you something about the mole. We know that the mole, the ancestor to this group of mammals, originated to North America by traveling across the Bering Land Bridge. So North America was once connected to Eurasia through the Bering Land Bridge when sea levels were much lower. So the first thing that I notice when I look at this species distribution map, we have an eastern population and a western population. They're separated by a continental divide. So they're separated by a mountain chain that runs north to south in North America. So we have two subpopulations on either side of a mountain chain. So we likely had a species or an ancestor arrived to North America by traveling on through the Bering Land Bridge, and then individuals of that species traveled in either direction on either side of the Rocky Mountains. We had a population go west and a population go east. And they're separated by a mountain chain, very little gene flow. Isolation creates conditions for evolution and speciation. You could also potentially invoke long-distance dispersal. Maybe the mole traveled across to North America by the Bering Land Bridge and originally went west, and then a couple organisms or individuals of that population managed through jump dispersal to get on the other side of the mountains and start a subpopulation on the east. That's another way you could potentially explain this distribution. All right, so the last one that we're going to look at is the gopher turtle in the southern United States. And we have examples from, and into Mexico as well. And we have examples from the southeastern United States, central, the Mexico region, and the western United States. So again, pause the video, take a minute to think about why this pattern of distribution might exist. All right, so we're back. We're looking at this distribution pattern. We have three patches. When I look at this, the first thing that comes to my mind, the first thing that I would look at, turtles tend to be very sensitive to extinction. We know that. We see that happening now. They're one of the most sensitive species to climate change, to human disturbances. So knowing that about the turtle, I look at this distribution. We have different shades of pink that tell us we have different subpopulations or subspecies. That tells me, or what that suggests to me, is that this might have been, at one point in its history, a continuous distribution. So unlike the gopher example, where the two populations were clearly separated by a geographic feature that still exists today, the Rocky Mountains, there might be, there's less obvious barriers here to separate these subpopulations. There might be climatic barriers if we were to look at it. So we could look and see if this species has very specific climate requirements, and if the climate in between these areas is unfavorable, would be one way of looking at it. Remember the spotted skunk example that we talked about when we were talking about the Pleistocene. Another option is that perhaps this had a much wider distribution. This species went extinct over large parts of its range and now only exists in isolated pockets that have now begun to evolve independent of one another and undergo evolution, or allopatric speciation. Okay, so those are disjunct species distributions. So just to recap, we've now covered three different types of species distributions. We've covered the cosmopolitan distribution, the endemic distribution, and the disjunct distribution. And the disjunct distribution type is particularly interesting for historical biogeographers because often these disjunct distributions tell us something about the influence of past events on the present day geographic patterns of species on Earth.